Yeah, it's working.
Perfect, thanks. So hello everyone. I'm Stefan Schult. I recently joined the strong lensing team at the University of Milan, but I'm presenting today some work mainly carried out by the Holy Smokes collaboration at the Max Planck Institute for Astrophysics. We've heard already now about strong lensing, which means we have a chance alignment such that we see a background object multiple of times. But now suppose we are very lucky and a supernova happens in this background object. That means we see now the supernova multiple of times and can actually measure the time delay when the supernova images appear at the Earth. This allows us to exploit these strong lensing systems for time delay cosmography, meaning we can measure the Hubble constant, or also use them to observe the supernova at very early times, meaning hours after the explosions. Now, how do we find them? With these large wide field imaging surveys like Hyper Suprime-Cam, but also in the near future with LSST or now also Euclid, we expect to find on the order of 100,000 of these strong lenses. And how do we find them? We are using machine learning, so we are very active on this topic. Here I'm just showing now the network architecture from one of our convolutional neural networks with a simple residual neural network. We're getting down the false positive rate now below 0.01% on real data. Or instead of just using one network, we are also for now searching for lensed quasars using ensemble networks where we combine several network architectures. I'm now showing here also some of the lens candidates which we found. But how do we analyze all these lenses at the end? And this was essentially a topic of my PhD. So we need the mass parameters of the lens, meaning the Einstein radius, the ellipticity of the lens, and so on. And there we can also use machine learning, meaning we train a residual neural network directly on the images and get out the parameter values from the network. This allows us to fully automate the modeling and bring down the computational time from several weeks down to fractions of a second. Given our involvement and work with convolutional neural networks, we thought, well, more or less every one of us needs redshifts. Normally, for photometric redshifts, you are extracting from the images some key quantities, like size, compactness, and so on, and feed this into your redshift pipeline, which can be machine learning technique. Or what we proposed, to skip essentially the catalog step and directly train a convolutional neural network on the images to get the photometric redshift. And it's working quite well, actually. Yes, I'm done. If you have any questions, I'm happy to, about all these topics which I flashed now, I'm happy to talk either now or later here. Yes.
Thank you so much, Stefan.